Here we have the chemistry paper written by the Matrix of November 2023. If you want to download the paper, just check the description below. Which one of the following represents a straight chain saturated hydrocarbon? So what is saturated? Well, we know that the alkanes are saturated. Okay, so let's do this. Alkanes, and then the other two, which is the alkenes and the alkynes, they are, so these ones are saturated, and then these ones are unsaturated. What does it look like? Well, you know, when you've got alkenes, you've got a double bond, and when you've got alkynes, you've got a triple bond. So let me quickly explain what saturated and unsaturated, what they mean by that. So if you have a saturated molecule, it's got hydrogens, and you've got something like this. Could you add any other hydrogens to this molecule? Could you just add another one here maybe? No, because each carbon must be surrounded by 4. So you cannot add any more hydrogen to this. So we say that it is saturated. It is completely full. You can't add any more. That is what saturated means. Unsaturated means it's not full. So what that would look like is if you had a double bond, then remember you'd only have one hydrogen and then 2 hydrogens on this one. So you can see that this carbon is still surrounded by 4 bonds, 1, 2, and then this counts as 2 over there, so that's 4. Now if you wanted to add hydrogens, you could do that to this molecule. All you would do is you would break this bond over here, and that would then open up 2 extra parts, and then you could add hydrogens. So you see that this original molecule over here is not full. You could add more hydrogens if you wanted to. That is what we mean when we say unsaturated. Okay, so if you had to go draw these out, you would see that none of these are saturated. However, this one over here, you can see it's got the perfect N and then 2N plus 2. If you wanted to draw it out though, that's fine. You would realize that this is the one that is saturated. So this is the answer, D. Which one of the following is a secondary alcohol? Okay, let's talk about that. I'll show you what a primary, secondary, and a tertiary alcohol actually is. So primary, secondary, tertiary. Okay, so let's quickly draw this out for you. Right, what I want you to do is look at the OH. Then I want you to look at the carbon that is attached to the OH, which would be this one. Then I want you to count how many carbons are touching this one. Well, that would only be over here. So there is only one carbon touching, okay, which is this one over here. Now, if we look at this molecule, so step 1, I want you to look at the OH. Okay, so you look at the OH. Step 2, look at the carbon touching the OH. Step 3, look at how many carbons are touching that one. Well, there's one over there and there's one over there. That is what we mean when we say a secondary. Now, as you can imagine, tertiary, let's quickly show you what that looks like. And then obviously hydrogens everywhere. Just to save time, I'm not going to put all the hydrogens in. Step 1, look at the OH. Step 2, look at the carbon touching the OH. Step 3, how many carbons are attached to that one? 1, 2, 3. That is the difference between a primary, secondary, tertiary. You can also use this when you are looking at primary, secondary, and tertiary haloalkanes. Right, so the question says, which of the following is a secondary? Now, I've been teaching for a long time. You would consider that I know science and maths very well. I still struggle to look at these things and know which one it is. I physically go and I draw them out. I don't like condensed formulas. My brain or my mind struggles to visualize it. So don't try to do it unless you really have a good skill at doing that. Okay, so I like to draw it out. So this one has a carbon, and then it's got 3 CH3s. So 3 CH3s attached to it. So there's 1, there's 2. Okay, so it's definitely not going to be this one, because this one is going to have an OH over here. This is going to be a tertiary. This is actually exactly the same as this one. So it's not going to be A. That's not our answer. Okay, it's good practice to draw it out while you're studying though. Right, let's have a look at this one. Here we have a CH3, so let's draw a CH3. Then we've got a CH2, but there's 3 of them. Okay, I've done this a bit weird. Let's do our CH3 like this. So there's a CH2, but then there's 3 of those. So that just means CH2, then another one, and then another one. Another one, DJ Khaled. And then OH. So this is a primary, because here you've got the OH, then you've got the carbon, and then how many carbons are touching this one? Only 1. Some of you are going to say, no, but there's 3. No. How many are physically touching that carbon? Only this one, okay? You can't say that this one is touching that carbon. They're not directly touching each other. That is what we mean. Okay, so it's not B. Let's have a look at this one. So we start with the CH3. Then we've got 2 CH2s. So that just means CH2, then another CH2. Then we've got a carbon, okay, which is attached to an OH. Okay, how does that even make sense? Oh, never mind. It's attached to a hydrogen, and then there's a double bond oxygen. So that's actually an aldehyde. So it definitely ain't you. So it's definitely going to be this one, but let's go draw it out just to make sure. So it's got a CH3, then it's got a CH2, then it's got a CH, and then there's an OH. So we'd put that over there. And then there's a CH3. Okay, good. So if we look at the OH, look at the carbon touching the OH. How many carbons are directly touching that one? 1, 2. Secondary. Perfect. And so the answer for this one is D. Which one of the following is a hydrolysis reaction? Okay, so hydrolysis, let's quickly talk about all the reactions that we've learnt about, if you've seen that table of mine. So we start with alkanes up at the top here. Then we put haloalkanes over here, alcohols, and then alkenes. Right. Now, we know that hydrolysis is when you go in this direction over here. It is the conversion of a haloalkane to an alcohol. And you could do that using, for example, water. You could use sodium hydroxide, potassium hydroxide. All of that is hydrolysis. So here we can see we've got an alcohol, so we don't want to start with an alcohol. Here we have an alkene, we don't want to start with an alkene. Here we have an alkene, we don't want to start with that. We want to start with a haloalkane and convert it to a alcohol. So the answer is A. Hydrochloric acid reacts with excess zinc. Okay, so here's the reaction, and we know that the zinc is in excess. Okay, that's interesting. Normally it's the liquid or the aqueous that's in excess. So here we've got the zinc in excess. Different reaction conditions are shown in the diagrams below. The mass zinc used is the same. So here we're using 100 centimeter cube of a 0.1 molar per, or 1 mole per decimeter concentration, and we've got zinc powder. Here we've got zinc lumps, and here we're using 200 centimeters cube, but we're keeping the concentration the same. How will the initial rate of the reaction and the final volume of hydrogen produced in test tube Y compare with that in test tube X? Okay, what we can actually do is let's ignore the initial rate of the reaction right now. Let's talk about the final volume of hydrogen. So we can see that we produce hydrogen over here. Now, because the zinc is in excess, when will the reaction finish? The reaction will finish when your limiting reactant has run out. Okay, so reaction will be complete when HCl has run out. So what we can do is, if you look at this one, if you use C equals to N over V over here, and then you change it to N equals to C multiplied by V, if you work out the number of moles of HCl over here, you would get concentration as 0.1. Volume would be 0.1, because remember, this must be in decimeters. And if you had to work this out, you'd get 0.01 moles. So then you would have 0.01 moles of HCl. if you look at the moles over here, it would be exactly double. You can go work it out, but you would get that there would be 0.02 moles. So then can we see that in this scenario, we have more moles of HCl? So from the equation, if we know we have more moles of HCl, the reaction will go on for longer, and that means you will be able to produce more hydrogen gas. So we're definitely going to produce, how will the produced in test tube Y? So in test tube Y, we're definitely going to produce more of hydrogen gas. And so we cannot choose C and we cannot choose A as our answer because we want the hydrogen gas to be more. Okay, now, because we're using lumps versus a powder, you got to think about what that looks like and how that will affect the reaction rate. We know that a powder is much faster, right? If you have something in a powder form, it's got a larger surface area, the reaction, more collisions take place, it happens faster. Whereas if you have lumps, it takes place a little bit slower. So in this one, we're definitely going to have a slower reaction rate. So the answer is going to be this one where it has lower. And so the answer is B. The diagram below represents a mixture of NO2 and N2O4 molecules. And then here they've given us a key. Okay. And at equilibrium in a 1 decimeter container. Okay. They are at equilibrium. The balanced equation goes like this. Okay. Now it says, which one of the following is true for the value of the equilibrium constant at this specific temperature? Okay, so we know that Kc is always equal to the ratio of your products over your reactants at equilibrium. This must always be at equilibrium. It's called an equilibrium constant. So if we look at the products are always the one on the right hand side. We can see that that's the white balls. So if you look at how many white balls there are, there's 1, 2, 3, 4, 5, 6. Whereas if you look at the number of reactants, which is the black balls, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 of those. Okay, and only 6 of these. Now, so immediately you can see that the concentration of the black balls is much larger. So this value at the bottom here is going to be a much larger value, and it's going to be to the power of 2. If you remember how Kc works, it would be to the power of 2. This is going to be quite a small value, and it's just going to be to the power of 1. So the numerator is going to be very small, the denominator is going to be very big. Mathematically, that makes this Kc small. So it's going to be very small. So it's not going to be 24. It's not going to be bigger than 1. It's not going to be equal to 1. It is going to be somewhere between 0 and 1, definitely. It can't go negative, so the answer is D. A reaction is at equilibrium in a closed container according to the following equation. Okay, the volume of the container is now increased while the temperature remains constant. Okay, so the volume of the container is increased. Visualize that. So if you have a container, situation 1, now in situation 2, they've made the volume larger, okay? So what that does is it will lower the pressure, okay? So the pressure is definitely going to be lowered. So it says the volume is now increased while the temperature. Which one of the following combinations is correct for the new equilibrium? Okay, so we know that when volume increases, pressure decreases. So that's the change. That is what the change has, that is what has been done to the system. How will the system respond? System will try to increase the pressure again. Okay? So when a system tries to increase pressure, how does it do that? It does this by favoring more. It does this by trying to make more gas molecules. It does this by favoring the reaction which makes more gas. Okay, so if you look at the equation over here, you've got solid, and then gas. So there's only gas on this side. So the system is going to go in the forward direction because as it goes in the forward direction, gas is a product. So that is what is going to happen. someone's going to come along and they're going to increase the volume. The system's going to be upset and it's going to be like, okay, no, I need to get back to the way it was. So I'm going to go in the forward direction. So what is going to happen to the concentration of oxygen? Well, that's quite an interesting one. Let's quickly go over to here. So the number of moles of oxygen. So we know that definitely if your reaction goes in this direction, the moles of oxygen are definitely going to increase. So we're not going to choose A and we're not going to choose B. Then what is going to happen to the equilibrium constant? Well, remember, the only thing that can change equilibrium constant is the temperature. A change like this is not going to affect the equilibrium constant. Yes, these are going to become larger. They're going to become more like their moles. And yes, this is going to become less. But the concentrations are not really going to be, the ratio of the concentrations is going to remain constant. Remember that temperature is the only thing that can affect Kc. And so, yeah, okay, that doesn't really help us, does it? Because both of those, say, remains the same. And so it is a bit of a tricky one thinking about the concentration of oxygen, but we know that if the reaction goes in this direction, we're definitely going to make more oxygen. So that's why we said for the moles, we said the moles is definitely going to increase. However, we know that the amount of this or the concentration of this can't decrease. It can't go down, especially because the forward reaction is being favored. And so we'll eliminate that option. And so the answer for this one is C. Nitric acid and ethanoic acid of equal volumes and concentrations are compared. Consider the following statements regarding their solutions. They have different pH values, both of the same, blah, 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 both solutions. Okay, so they're just stating a whole bunch of stuff. Which statements are true? Okay, so because they've given us equal volumes and concentrations, can we also say the moles are the same? Yes, because we know from this formula, if you get moles by itself, then you get that. And if the concentrations and the volumes are the same, then the moles are the same. So we've got equal moles of HNO3, which is, remember, a strong acid by definition. You just have to know that. And CH3COOH, which is a weak acid. So if I give you equal moles of each one, we know that the strong acid would ionize completely in water, whereas this one would not. So this one, the HNO3, would cause the solution to become very acidic, which means, whereas this one would not have the same pH. So their pH, they have different pH values. That is definitely going to be true. So let's put here, that is true. Conductivity. So we know that when you put HNO3 in water, it ionizes completely to become NO3 minus plus H3O plus. It is these ions that allow a solution to be able to conduct electricity. But now when you do the ethanoic acid, it also ionizes in water. It produces CH3COO minus plus H2O. Plus H3O. However, we know that this reaction doesn't really want to take place in the forward direction, and very often this one actually ends up going, it always ends up going also in the reverse direction. So the amount of ions you will produce with a weak acid is not going to be nearly as the same as the amount of ions you can make with a strong acid. So in the strong acid, you will have more ions. So this one is a better electrical conductor. Strong acids are better electrical conductors because they produce more ions. Okay, so both have the same electrical conductivity. That is definitely false. Both solutions require the same number of moles of KOH for complete neutralization. Okay, well, we'll have to check the reaction to see if the ratios are 1:1. So if you take nitric acid and you react it with KOH, here we go, acid plus a metal hydroxide. What are the products? A salt and water. So let's put the water, and then the salt is just going to be the K and the NO3. Now, the valency of K is always +1, and you need to know your polyatomic ions, that's also -1. So this molecule is perfect. You don't need to put a 2 or anything like that. Now, if you balance it, you would see that on the left-hand side, we've got 2 hydrogens, and on the right, we've got 2. For the NO3s, you can see it's all balanced. For the Ks, the oxygens is 4 and 4. So this thing's completely balanced. Let's now look at the ethanoic acid. It's also going to be a salt and water. So the salt will be K and then CH3COO. Now remember, this thing is still +1. This whole thing is still -1. And so if you had to go look at this reaction, it is all completely balanced. So for every 1 mole of HNO3, you need 1 mole of KOH. And for every 1 mole of CH3COOH, you need 1 mole of KOH. There's no 2's in the front here or anything like that. So both solutions require the same amount of moles for complete neutralization. Yes, so that is true. So the things that are true would be 1 and 3. So 1 and 3. So the answer is C. The apparatus in the diagram below is used for a titration with HCl and KOH. In a titration, the learner accidentally exceeds the endpoint. Which one of the following will be true? Okay, very, very easy question. We know that if you have a perfect HCl and a perfect KOH titration, this is a strong acid with a strong base. Then if the learner was very careful when they were letting the drops go inside, at the point where, if they got it perfect, then they would see the color change and immediately they would stop and the pH would be exactly equal to 7. Okay? But what they tell us is that this learner exceeds and they let too much of the HCl in. So what will happen is that all of the KOH will be neutralized, but now there's going to be extra HCl that they're going to add after the titration is finished. So because they're adding more HCl, which is a strong acid, the pH is going to be more acidic. So it's definitely going to be less than 7. So it cannot be this one and it cannot be this one. Now, what you must remember is that acids are a source of H+. So because we're going to have more acid, the H+ concentration is going to be larger than the OH- concentration, which is from the KOH. Now, what we must remember is that acids are a source of H+. So because we are going to be adding in excess acid, the H+ concentration is going to be larger than the OH- concentration, and so the answer for this one is A. The following hypothetical reduction potentials relate to a galvanic cell. Consider the following statements. The EMF of the cell is 0.20, electrode Y is the anode, X is oxidized. Which of the following is true? Okay, so we should know that the one that has the largest voltage, that's going to be your reduction reaction. Reduction, and that's also going to be your cathode. And then the one with the smaller voltage, that's going to be your oxidation or your anode. Okay, so if you wanted to work out the EMF of the cell, we know that there's a formula that says it's the cathode minus anode. And that's going to give us 0.10 minus negative 0.10. That's going to end up becoming 0.20 volts. So they said the EMF is 0.20, so that is correct. This is true. Now, it says that electrode Y is the anode. Well, yes, that is also what we said over here, so that is true. So for number 3, it says that X is oxidized. Well, that's not true because we said that this is the reduction reaction. So, and X is one of the products. So there's no reduction so there's no oxidation taking place over here. And so this one is false. And so the correct answer would be B. Which one of the following half reactions below will be the main reaction at the anode during electrolysis of concentrated, copper chloride? So if we have a electrolytic cell, we've got 2 anodes, typically made of carbon. Okay, and then you've usually got a battery source because it's electrolytic. So let's say that's the positive, that's the negative. And then you've got copper chloride, which is actually going to be broken up into its ions, which is going to be copper 2 plus and Cl minus. Okay, now we've also got water, because they said it is it's an aqueous solution. It's not a molten solution. So there is also going to be water. Okay. Now, we know that this one is negative. So it will naturally be attracted to the positive terminal. And then this one is positive. So it would naturally be attracted to the negative terminal. So this is that part where I've taught you guys about this, where you've got a concentrated solution and water is present. So water is going to compete. So let's try to figure out who's going to compete with who. So we can see that we have a Cl minus. So there's the Cl minus on our table right here at the bottom. Okay, so that's what we have. This is not the same as a galvanic cell where you would highlight this whole reaction. We don't have Cl2. We only have the Cl minus. Okay. Now, the water that competes with that one is going to be this one over here, okay? And so these two are going to compete to see who's going to go in this reaction to the left. Then on the other side, we've got copper 2 plus. Now, don't be careful. There's a copper 2 plus, but you want to find the copper 2 plus that goes all the way to copper. So that would be over here. So what do we have? We have copper 2 plus, and the water that competes on the left-hand side of the table is this one up here at 0.83. And so those two reactions are now going to compete to go in this direction. Okay. Now, going in that direction, when you've written it like that, that is reduction. And then when you write it like this, where it goes from right to left, that's oxidation. Now, they said, which of the following is going to happen at the anode? Now, I've taught you guys that reduction always happens at a cathode, and oxidation always happens at a anode. So the competition is going to be over here. Okay. Now, what have I taught you guys? I've taught you guys that normally you need to follow the arrows. Remember, there's always an arrow on the left side of table 4b that goes down, and then there's an arrow that goes up on the right hand side for table 4b. And we normally say that the one that is higher up will be the winner. So we would normally say that this is the winner. But I've explained in one of the videos that there is an exception when they use concentrated Cl. When there's a concentrated Cl, then it ends up being the winner instead of the water. Remember that. I've explained that. Remember? So the reaction that is going to happen is this one, but it's going to be written from right to left. So it's going to be this reaction over here. So D is the answer. Okay, so here they give us a table with a whole bunch of organic compounds. The first question says, define the term organic compound. We must understand that organic chemistry is built upon the foundation of carbon. So the answer is literally just compounds containing carbon. That's it. Now, write down the IUPAC name of compound E. Okay, so I always like to go and draw it out for myself. So there's a CH3. Then there is a C with an H attached to a CH3. Okay. Then there's a C with a double bond attached to a CH2. Okay, that's interesting that they're going like that. And then there's a CH3. Okay, so immediately we should identify that there is a double bond. And so your longest continuous chain has to include this functional group. So you actually can't go like this and say that that's the longest chain. It has to include the functional group. So that's going to be your longest chain over there. Now remember, because we have this functional group, we are going to name it from the side that is closest to that functional group. So this will be carbon 1, this will be carbon 2, this will be carbon 3, and this will be carbon 4. So on carbon 2, we have a one branch, we have a one carbon branch. Then on carbon 3, we have another one over here. So on carbon number 3, we have another methyl. And that's it actually. Those are the only branches we have. Now, we can see that the longest continuous chain is 4 carbons. So that's going to be bute. Now, the double bond is on carbon number 1, so you're going to do that. And then for the branches, you're going to say 2, 3 dimethyl, like that. Okay, the next one is, what is the name of compound H? Okay, so H is over here. That's a pretty easy one. You should identify that that is a ketone because it's got a carbon double bond over here. So why is it not an aldehyde? Well, because it's got a carbon double bond that is in between two carbons. Whereas if it was an aldehyde, then it would be on the side. Why? Because aldehydes are always on the side. Okay, you've probably heard me say that before. So this is an easy one. It's just a ketone. It's a 4-carbon ketone. So we're going to say bute. And then you're going to say butan, and then you're going to say where the double bond carbon oxygen is. So it's on carbon number 2, because you always name it from the side closest to the functional group. So like that, and that's going to be 1. And then there's no branches, and so that is the name. Okay, write down the structural formula. So when they say write down, it's a bit confusing. It actually means draw. So draw, because structural formula is when you draw it out. So compound B. Okay, so compound B has a CH3. Then there is, okay, I'm going to need more space. Okay, we've done the CH3. Then there's CH2, but there's 3 of those. So what that looks like is this. Okay, so now we've gone up to there. Then there's a carbon. Okay, so we put a carbon. And then there's this double bond oxygen. That only happens in esters. So it's going to be a double going like that, and then something like that. That is how an ester goes. Whenever you see that COO like that. If it was COOH, then it would be a carboxylic acid. But it's not COOH, it's just COO. And then at the end of that, there's a CH3. Now remember, I'm not going to go put any hydrogens around these oxygens. And so that is what that molecule would look like. That is for the structural formula of compound B. Then what is the structural formula for compound C? Let's do that one. Okay, so that is going to be, it's a hexane. So that's 6 carbons. 1, 2, 3, 4, 5, 6. On, let's just call this carbon 1, 2, 3, 4, 5, and 6. On carbon number 4, there is an ethyl. Now remember, ethyl means 2, so we put 2. Don't do this. Don't put 1 here and 1 here, because that's not ethyl. That's actually 2 methyls. So you want like that. Obviously, I'm going to put the hydrogens just now. And then on carbon 3, there's a difluoro. So that means on carbon 3, there's a fluoro there, and then there's a fluoro there. Okay, now the rest is just hydrogen. So fill that all in. Okay, so we've done this one. Now, what is the general formula of the homologous series to which compound E? So compound E is a alkene. We know that with a double bond. We already saw that one earlier. So we know that alkanes, they have CnH2n plus 2. Alkenes, they are CnH2n. And then alkynes, they are CnH2n minus 2. So they want this alkenes, and so you're going to say the general formula is CnH2n. This next question says, what is the structural formula for the functional group of F? Okay, so if we look at F is a ketone, because you see how it's got a carbon, double bond oxygen. Why is it not an aldehyde? Well, because the carbon double bond oxygen is in between 2 carbons. So when you do the functional group, it's not enough to just do that. You have to show that it's a carbon and a carbon on the other sides of this carbon. And so this is the answer. Okay, the next question says, what is the IUPAC name of the alcohol that you would need to make compound B? So compound B was the ester that we already drew out, so you guys would already have that. So I'm just going to quickly redo that one. Okay, and then obviously with hydrogens everywhere else. Just want to double check. CH3, then there's a CH2, 3 of those. Then there's a C double bond, oxygen, CH3. Yes. Okay, so what we must remember is that this is an ester. How do we make esters, guys? It is a alcohol plus carboxylic acid, and that is what makes an ester. Now, we need to identify that this part here with the double bond oxygen, that was the original part from the carboxylic, and then this part would have been from the alcohol. So we can see that the alcohol part only has one carbon, that is meth. So the alcohol would be methanol, methanol, or methanol. You can also say methan 1-ol, but methanol is also okay. Right. This question now says, write down the letters of the compounds that is a functional isomer of compound G. Now remember, with isomers we get three types: functional, chain, position. When it's functional, it means that it's totally different homologous series. Now the only types we get in grade 12 is ketones are functional isomers with aldehydes, and then carboxylic acids are functional isomers with esters. So if we look at G, we can see it's got that C double bond oxygen attached to an OH. It's got that COOH. That is a carboxylic acid. So the only way to have a functional isomer of this would be for it to be an ester. So write down the letters of the compounds that would be a functional isomer. Well, it would have to be some type of ester. Now, we do have an ester on our diagram, and that was this one. But let's just make sure that there's not another one. And let's just make sure that it all works. So in this one over here, we've got 1, 2, 3, 4. Oh, wait, I've got to be careful. There's 1, 2, 3, 4. Remember, there's 3 carbons over here. There's 3 carbons over here. So there's 5. There's a total of 6 carbons in this molecule. The hydrogens, there's 3 over there. This would give you 6, so that's 9 hydrogens, plus 3 over here, that is 12. And then the oxygens, there's 2. Now let's see over here. We've got 1, 2, 3, 4, 5, 6 carbons. Hydrogens, there's 3, 6, 8, 11, 12, and then 2 oxygens. Perfect. It's exactly the same. That is what isomers are. Isomers have the exact same molecular formula, but different structural formula. And that structure can differ in 3 different ways: functionally, positionally, or chain. But this one is the functional isomerism that they're talking about, and so it's going to be compound B. Write down the compounds that are chain isomers of each other. So chain isomers, they obviously also have the same molecular formula. Remember, that's always what happens with isomers, is they always have the same molecular formula, just like we see over here. But then, as we said, we get 3 different categories: chain, position, functional. So the first thing would be to realize that these two are not chain isomers of each other, so we can just scrap those out. We're looking for molecules that have the same amount of carbons, same amount of hydrogens, and same amount of everything. So heptanoic acid would have 7 carbons. This one would have, or let's go to hexanoic acid. Okay, they can't have the same. They definitely can't be the same. How many carbons do we have in this molecule? This is 1, 2, 3, 4, 5, 6 carbons. I'm just going to look at the carbons for now. This one's going to have 6 carbons. This one's got 1, 2, 3, 4, 5, 6 as well. Okay. And then this one's got 1, 2, 3, 4. And then we already excluded these, although maybe they'll be chain isomers with something else. So these ones we already said have 6 carbons as well, and then these ones have 6 carbons. Okay, so it definitely can't be, and then this one's going to have 6 carbons over here, but then it's also got ethyls, and it's got fluorines. Okay, it can't be this one. There is no other molecule that has fluorine, so you can't have the same molecular formula. Let's think about this. This one I'm going to exclude as well, because this one only has 4 carbons, but there is no other thing that has 4 carbons, so nothing would be the same as that one, so that one's out. This one's out as well. It's the only thing that has 7, so that's out. So let's now go look at some hydrogens. So this one over here has 3. Oh no, we already said it has 12 hydrogens, didn't we? And we said these ones also have 12 hydrogens. Hexanoic acid. Well, that's a carboxylic acid, where we will just put that on the last carbon, or on the first carbon, depending on how you think about it. 4, 5, 6. Okay, how many hydrogens would this one have? Well, it's got 3 here, 5, 7, 9, 11, 12. Okay, so this one's also got 12. And then it's got 2 oxygens. So did this one also have 2 oxygens. And so does this one have 2 oxygens. Okay, we're trying to find molecules that have the same molecular formula because isomers have to have the same molecular formula. So I know some of you are like, yeah, but Kevin, here, they got the same. Yes, but we just need to double check that it's going to specifically be chain isomerism. Okay, I think it's going to be this one and this one, because they're both carboxylic acids, which is good. You don't want them to be functional isomers as well. So if you look at hexanoic acid, when I drew it out, and then obviously hydrogens everywhere, if you look at the chain, how many carbons are there? The longest chain had 6. But if you look at this one, it's also a carboxylic acid, right? So that's perfect. But look at the longest chain. The longest chain is only 1, 2, 3, 4. So you see the chain is not the same length. That is what chain isomers are. So the answer here is going to be that D and G are going to be D and G are going to be chain isomers of each other. They are the same thing. They're both carboxylic acids, so they're not functional isomers. Functional isomers are different things like aldehydes and ketones or carboxylic acids and esters. But with chain isomers, they are very often the same thing, but the chain, the longest continuous chain, is a different length. The relationship between boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated. P, R, and S are obtained. All compounds used are straight chain molecules. Okay, so before we start, let's just try to understand what they're doing here. So on the x-axis, we've got the molecular mass, okay? And then on the y-axis, we've got boiling point. Now, we know that as you increase the molecular mass of a molecule, we know typically that boiling point will increase. And that's what we can see over here, right? Mainly because of London forces. The bigger the molecule, then typically the London forces are increased because of the larger surface area and all of that. And so with stronger London forces between the molecules, they become a lot more difficult to boil. And so with increased molecular mass, the boiling point tends to go up. So the first question says, define the term boiling point. So don't say it's the temperature when a liquid turns to a gas. It is that, but that's not the formal definition. The formal definition is, it is the temperature when the vapor pressure of a substance is equal to atmospheric pressure. Okay. Write down, okay, so we've done this one. Now it says write down the conclusion that can be made for curve P. So curve P, what we can see is that as the molecular mass increases, the boiling point increases. So we can say boiling point increases with an increase in molecular mass. Okay, this one says, explain the answer to question 3.2 in terms of the structures of the compounds. Okay, so we know that we're mostly looking at aldehydes, carboxylic acids, and primary alcohols. So for example, let's say we're looking at a specific alcohol. Let's say we're looking at propanol, propan 1-ol. Okay, it's going to be on carbon number 1 because they said it's a primary alcohol. So for example, propanol looks like this. Okay, now let's say for example that is this position over here. Then what would these next dots be? Let's just pretend that this line is alcohol. I'm not saying that it is, but let's just pretend this is alcohol. And let's say this is propanol. Then what would this be, for example? Why would the mass increase? Well, then they would go up to butanol, for example. Let's say butan 1-ol. So then all that happens is you don't add another OH. What do you add? you're just adding another CH3 at the end of the chain, and that would maybe be there. And then you see how the mass would begin to get larger. And then how do you get another alcohol? Maybe you go to pentanol. So that's going to be 5 carbons now. Still going to be 1 OH. So you can see that that is what they're doing. They're just taking, for example, alcohols, which probably isn't going to be this one, but let's just pretend. And that is how they increase the mass. They're just stepping up through the homologous series. They're just adding an extra carbon, adding an extra carbon. And what we are noticing is that the boiling point is going up. So why would the boiling point go up from here and then to here and then to here? Well, let's get into the details. So if we look at propanol, for example, and then we're going to look at butanol. Okay. With propanol, it's always good to draw 2 of them because that is what intermolecular forces are. It's the forces between the molecules. So I'm going to draw another one now. Okay, so here we have 2 propanol molecules. We've got one here and we've got one here. Now we know that alcohols have hydrogen bonding. We can see we've got hydrogen bonding. So this section over here is going to have hydrogen bonding. There's also dipole-dipole because of this part over here. That forms a dipole and that forms a dipole. So there would be a dipole-dipole as well. Okay. And then this area here, these alkyl areas where it's just carbon and hydrogens, well, we know that those areas are non-polar. So we know that in this section over here, it's pretty much just your London forces. London forces. Now, if I had to go and draw butanol, so I'm going to have to draw 2 of those. Well, then once again, you're going to get hydrogen bonding over here. You're also going to get the dipole-dipole because of these parts. Okay, so you're also going to get dipole-dipole. But can you see that that is going to be the exact same in this scenario and in this scenario? There isn't more hydrogen bonding over here, and there isn't more dipole-dipole. The difference is that if you look here, look how long this London force area is now. See, because now we've got 3 carbons in this part over here. So now you're going to have London forces as well, but you've got London forces over a larger area. And that is the difference that we are seeing with these curves. As you add more carbons and hydrogens, the molecular mass begins to increase. But with that, you add more space for more London forces. And so your boiling point, because the forces between the molecules become stronger, it would be more difficult for you to boil this one because you would have to overcome more London forces. Okay? And that is why with more molecular mass, we are noticing that the boiling point is increasing. So for 2 marks, it says explain the answer to question 3.2. So why is the boiling point increasing with an increase in molecular mass? We can just say, as the molecule's chain is extended, there is a larger surface area for London forces. Then we can say, therefore, more energy needed to overcome the forces of attraction between the molecules. Okay, so let's just clear up a little bit of space. They tell us that curve R is the alcohols. Then they say which homologous series is represented by curve S. So what we have is we've got aldehydes, alcohols, and carboxylic acids. So if we look at aldehydes, for example, so I'm going to draw a 3-carbon aldehyde. These are all just hydrogens. And then I'm going to draw another one, because whenever you look at intermolecular forces, you always have to look at that. Okay. Now, in between this area here, these areas here, we know that that's London, because those are the non-polar areas. Then between this and this, you're going to get a dipole-dipole. There's no hydrogen bonding with aldehydes. Okay? Now, if we look at alcohols, so these are your aldehydes. If we look at alcohol, let's quickly draw 2 those. Okay. So once again, between these areas, that's your London. Then over here, and over here you've got a dipole. This is a polar section because carbon is less electronegative than oxygen, and so it causes the oxygen to become negative and the carbon to be positive, and so you get a dipole-dipole attraction over here. Dipole. But then with the OHs though, between those, there's also a hydrogen bond. Okay, so if you had to compare aldehydes and alcohols, you would notice that alcohols have higher boiling points if you are comparing the same amount of carbon. So here we have a 3-carbon aldehyde, and here we have a 3-carbon alcohol. Alcohols would have a higher boiling point because they also have to overcome these hydrogen bonds, okay? And now if we look at carboxylic acids, okay, so let's do a 3-carbon carboxylic acid, and then here's another one. Okay, so with carboxylic acids, they also have this non-polar part over here. So in that area there, you've got London forces. Then you've got these areas over here, which produces a polar section. So there you're going to have your dipole-dipole. And then you're also going to have hydrogen bonding, for example, over there. So some learners will think that alcohols and carboxylic acids are therefore going to have very similar boiling points because they've got pretty much equal London forces. They've got one dipole-dipole, or like pretty much one area where there's dipole-dipole, and then there's hydrogen bond. However, carboxylic acids actually produce 2 hydrogen bonds for every 2 molecules that come into contact with one another. If I draw a carboxylic acid a little bit different, so if I put a carboxylic acid like this, and like that, and then I put another one, let's put this one like that, and like that. So and then you could imagine it would have the rest of its molecules going whatever. Okay, so what actually ends up happening is that there is going to be a hydrogen bond over here between this hydrogen and this oxygen over here. So there's a hydrogen bond. And then it's going to happen over here where you've got this hydrogen and that oxygen over there. And so for these 2 molecules, it produced 2 hydrogen bonds, whereas with alcohols, they only produce 1. So carboxylic acids will always have the highest boiling point between aldehydes, alcohols, and carboxylic acids, as long as you're comparing the same amount of carbons, 3 carbons in each of these. Then carboxylic acids will always have the highest boiling point, meaning that they are the most difficult to separate from each other, and that's because they've got the London forces and the dipole-dipole, just like the other ones, but they also have 2 hydrogen bonding scenarios for every 2 molecules, whereas with alcohols, they only have 1 hydrogen bond scenario for every 2 molecules. So then what we would expect is that the lowest line, that's definitely going to be your aldehydes. They're going to have the lowest boiling points. Then you're going to have, your next one is going to be your alcohols. And that's even what they said. They said R is the alcohols. And then the highest boiling point line would be your carboxylics. Okay, and so they said here curve R is the alcohols. Which homologous series is represented by S? That would be aldehydes. Okay, and then it says explain by referring to the strength of the intermolecular forces. But it's only for 2 marks, so we're not going to go into the details. We're just going to say that aldehydes have the weakest intermolecular forces out of the 3 molecule types. Okay, therefore less energy needed to overcome the forces of attraction. So then they have the lowest boiling points. They have lowest boiling points. Remember that the boiling point is the energy. So if you need a lot of energy to separate something, then you have to make the boiling point very high, because the boiling point is the temperature, the energy, the temperature, or the energy from the temperature is what you are using to boil the substance. So if something has a high boiling point, it means that you need to raise the temperature very high in order to have enough energy to be able to overcome the forces of attraction. But if the things like aldehydes have very weak forces, then the boiling point doesn't have to be that high, because it's not necessary to have that much energy to be able to separate the molecules from each other. Because when you are boiling, you are going from a liquid where the molecules are nice and close to a gas where the molecules are far apart. So to be able to move them from a liquid to a gas, you have to move the molecules apart from each other. And for that, you need energy to separate them, because they're holding onto each other because of the intermolecular forces. So if the intermolecular forces are strong, then you need more boiling point or more energy. And if the intermolecular forces are weak, then you don't need such a high boiling point, because you don't need as much energy to separate them. Okay, now it says for curve R, which is the alcohols, write down the molecular mass of the compound with a boiling point of 97. Okay, so we go to a boiling point of 97, so that's going to be somewhere around here, but let's just double check. So this is probably 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. Okay, so it's going up in fives, so 95 is here, so 97 is sort of in the middle there. So you'd go in the middle, boom, it's that one over there, and then you would come, then you would go down, there. Okay, so now we got to see what is the molecular mass. So it's probably 60. It looks like it's directly in the middle. 52, 54, 56, 58, 60. Yeah, it's exactly 60. So you could just say the molecular mass in, just use these units over here. So you could just say 60 grams per mole. Now it says, what is the name of that compound? Now that's an easy one, because we know that it's primary alcohols. So it's just alcohols with the OH on carbon number 1. So let's take a guess. I know that every carbon has a mass of 12, and I know that oxygen has a mass of 16. So if we chose a 3-carbon alcohol, well, then you would have 3 carbons, which is 12, 24, 36, plus oxygen is 16, so that's 50, and then you've got a whole bunch of hydrogens. So maybe that'll get us to 60. So let's try a 3-carbon alcohol. Okay, so I know that would have 3 carbons, that's 12. Each carbon has a mass of 12. I'm getting this from the periodic table, right? Then it's got 1 oxygen, and then it's going to have how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so if you work this out, you get, oh, I made a bit of a mistake here. I said 12, 24, 36, it's 52. But 3 times 12 plus 16 plus 8, oh, it gives us exactly 60. So it must be a 3-carbon alcohol. So you could say propan 1-ol. If it was a 4-carbon, then the mass would go too high. If it was a 2-carbon, then the mass would be too low. But they want the mass to be 60. Okay, now this question for 3 marks says, 2 compounds, A and B, used in the investigation have a molecular mass of 74. Okay, so they have a molecular mass of 74. So let's go straight to that. A molecular mass of 74 is here. And let's draw a line going up. Okay. Now, it says A has a boiling point of 118. So 118 is probably this one over here. Okay, so it's the alcohol. See that? It's because it's coming from the alcohol curve. That would be about 118. And B has a boiling point of 142. Okay, well, that would have to be the carboxylic acid, because that's somewhere up here. So it's definitely not the aldehyde. Explain the difference in the boiling point by referring to the structures. Okay, fantastic. So that is what we spoke about over here, where we're now going to be comparing alcohols and carboxylic acids. So all that they want you to say here is that carboxylic acids have 2 sites or places for hydrogen bonding. Alcohols only have 1 site for hydrogen bonding. Therefore, more energy needed to overcome forces of attraction between the molecules of carboxylic acids. Consider the cracking reaction below. So we know that cracking is when you take a long molecule and you break it up into smaller molecules. You crack it, you break it into smaller molecules. The first question says, define cracking. It is the process during which long chain alkanes are broken up into smaller molecules. Write down the values represented by X, Y, and Z. Now, this is no mathematical formula. This is literally just balancing an equation. So we know that there's 16 carbons on this side. Here we've already got 12. So if those already add up to 12, then we still need another 4. But because there's a 2 there, you mustn't put a 4 here by Y. You're just going to put a 2, because then it's 2 times 2. So then the carbons would be balanced. So Y is 2. Okay, now to find X, just look at the hydrogens. There's 34 of them, 34 hydrogens. So there's already 14 over here. And, okay, we know that this is a 2. But now we've got 2 unknowns. Okay, but what we must realize is that this over here is an alkane. So this is an alkane. How do I know that? Because if I know that this number is double that number plus 2, because 16 times 2 is 32 plus 2 is 34. So that's an alkane, because I know that alkanes they've got that general formula. Here I can see we've got another alkane, because if I multiply that by 2 and I add 2, it's the same. So this is also an alkane. But I know that when I crack, it always gives an alkane, and then alkenes are the other ones typically. So I know that alkenes have the general formula like that. So I know that this must be double. So this would be 12. Okay? And then I know that if this is then 2, then this would have to be a 4. And so we could then say that Y is 2, X is 12, and Z is 4. Compound C6H14 undergoes complete combustion. That's when they reacted with oxygen. Using molecular formula, write down the balanced equation for this reaction. Okay, this should be full marks for all of you. Combustion reactions are very easy. All you do is you take the molecule C6H14, you react it with oxygen. The products must always be CO2 and water. And what have I always told you guys to do first? Balance the carbons first. So there's 6 on this side, so put a 6 over there. Then balance the hydrogens. So there's 14 on this side, so you would have to put a 7 over there to make 14. And then balance the oxygen. So don't worry about this one. Use these two. So on this side, you've got 6 times 2, so you've got 12 oxygens over here. And then you've got 7 oxygens over here. So you've got a total of 19 oxygens on the right. So what would you have to multiply this with? Well, you would have to multiply it with, what is half of 19? Half of 19 is 9.5. So you'd have to multiply this by 9.5. Okay, because 9.5 multiplied by 2 would then give you 19. However, you don't want to leave your answer with decimals or fractions. So what we'll do is we'll multiply everything by 2. So it'll become 2 C6H14. This multiplied by 2 would become 19. This multiplied by 2 would become 12. And then this multiplied by 2 would become 14. And there is your final answer. Consider the equations for the reactions 1 to 3 below. A and B represent organic compounds that are positional isomers. X is an inorganic product. Okay, so what is the definition of positional isomers? Well, let me show you what positional isomers are. Let's say we're looking at alcohol, and we've got an alcohol like this, okay? And then let's say we've got another one that also has 3 carbons, but this alcohol, the OH, is on carbon number 2. If you had to go add up the number of carbons, there would be 3 for both. The number of hydrogens would be 8 for both. And the number of oxygens would be 1 for both. But they are 2 slightly different kind of molecules. We call them isomers because they've got the same molecular formula, but you can see that their structures are different. We can see that the position of the function group here is on carbon 1, here it's on carbon 2. That is what a positional isomer is. It's the same type of molecule, like an alcohol and an alcohol, but the position of the functional group is on a different position. Okay, here it's on position number 1, here it's at position number 2. Okay, so if you had to define positional isomers, you would say that they are molecules with the same molecular formula as we can see over here, for example, but having functional groups in different positions in the molecule. Okay, right. Now, this question, what is the type of reaction represented by number 1? Okay, so what we can see at reaction number 1 is we've got it's probably an alkene. Let's have a look. You have a CH3, so let's quickly draw out a CH3. And then you've got a CH2. Okay. Then you've got a CH, and then you've got another CH, and then you've got a CH3. So you see how this carbon and this carbon only have 3 things around them. So to fix that, we make it a double bond. So what we have here is an alkene. So immediately, if you know your reactions very well, you need to think, what do alkenes like to do? Alkenes like to have addition reactions where you add things onto them. For example, you break this, and then you can add a hydrogen, and you can add an OH, and then you make an alcohol. Or you could add a hydrogen and a chlorine, or you could add 2 hydrogens, or you could add 2 chlorines, for example. Alkenes are keen to react, and they love to do addition reactions. So here we can see that we've got that. We're going to add it to this one, and it's going to be some type of addition reaction. The only thing that makes this question confusing is usually there would only be one product over here, but they're doing something weird, but we'll obviously get to that. But yeah, it's addition. You can just call it addition, but you can also be more specific if you want. You could say hydrohalogenation if you would like to do that. Okay, now it says, what is the structural formula of compound B? So do you know what I think they're doing with A and B? You know, sometimes with like Markovnikov's rule, we have to say that the rich get richer and the poor get poorer, and then you get a major product and a minor product. I think they're showing both of them here. I think. We'll figure it out as we go, but I think they're showing the major and the minor product. So we know that when you take this molecule and you add HCl, okay, when you add HCl, we know that the hydrogen is either going to go, for example, there, or it's going to go there. Although in this scenario, it's pretty equal. Can you see that it's equal on both? Because normally you would see how many hydrogens are attached to this one and how many are attached to this one, and then the richer get richer and blah, 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 blah. But in this scenario, it's going to be equal. So in one of the scenarios, you're going to have an H over here, and you're going to have a Cl. And then in the different scenario, you're going to have it the other way around, where the Cl goes that side, and then the H goes to the other side. That's probably what they are showing here. We will figure that out as we go along. Okay, but we don't know which one's which. We don't know which one's A and we don't know which one's B. We're probably going to have to use this reaction and try to work backwards to figure that out. And that is also why they said that A and B are position isomers. We can see that these are the exact same molecules, right? Same carbons, same hydrogen, same everything. But here we can see that the Cl is on carbon number 2, whereas here we can see the Cl would be on carbon number 3. So that is a position isomer. So I think we are correct in saying that it's the 2 different products over here. But now we still don't know which one's A and which one's B. There's going to be a specific way to know which is which. So we're going to have to probably look at this molecule and then reverse engineer the whole process and try to figure out how this happened. So let's go draw this molecule out, which is, it's got a CH3, then it's got a CH2, then it's got another CH2, then it's got a CH with an OH attached on the other side over here, and then it's got a CH3. So because we now know that this molecule is this one over here, it gives us a better idea what A would be. We know that this OH is going to replace the Cl. So we can see that the OH is on carbon number 2. So A must be this one over here. Because then, if you had that, let me just quickly draw that out for us. 3, 4, 5. And then on carbon number 2, there's a Cl. Then when these two things, when this reaction takes place, you would get the Cl switching place with the OH. And so we can see they're both on carbon number 2. So if A is the one that then has it on carbon number 2, then B must be this one over here. And so once again, if A is this one where it's on carbon number 2, then B is the other one where it's on carbon number 3. So it says, what is the structural formula of compound B? Then you would just go draw that in, the 5 carbons, and then you would put on carbon number 3, you would put the Cl, and then you'd put H's everywhere else. So you see how we had to look a little bit from here into the future to see what happened in this reaction to give us a better idea of which one is A and which one is B. Okay, so there's our answer over there. Okay, so we've done this one, we've done this one, we've done this one. Now it says, what is the formula of X? Now they tell us that X is a inorganic product. Inorganic means there's no carbon involved. Man, I should have kept the alcohol one that I had, but let me just quickly draw it here anyways. We have lots of time, don't we? Meanwhile, you're sitting there, you're about to go write your exam. OH, and then CH3. So all that happens is we had an H2O. You see we had an H2O. So let's just say here, H2O. All that happens is that this OH is going to replace this Cl, and that's why the OH ends up over there. And then the Cl would obviously just go and join up with the hydrogen again, and so that would be the product, HCl. So that is the inorganic product. Whoops, HCl. Okay, this question over here now. What is the inorganic reagent used in reaction number 3? So in reaction number 3, we are taking, is it exactly this one? CH3, CH2, CH2, CH. Yeah, so we're taking that molecule again. Let's go draw it out again. I apologize. And we are converting it into this. Okay, so we're converting it into CH3, CH2, CH, CH, CH3. Okay, so this is an alkene because here we would have to put a double bond. Okay, so we are doing some type of elimination because what we can see is we're starting with this and then we are getting rid of water and one of these hydrogens, and so that's why we're forming a double bond here. Okay, so whenever we do elimination, well, whenever we, for example, we dehydrate an alcohol, which this one is, and we dehydrate it, we typically use a catalyst, and that catalyst we use is typically going to be H2SO4. So it says, what is the inorganic reagent for reaction 3? I would just say H2SO4, or sulfuric acid, whatever you want to call it. Okay, we're here now. It says compound A can be converted, so remember what compound A looks like, can be converted directly to the organic product of reaction number 3. Okay, so let's go check what they're saying here. Let's see what they are actually talking about here. Right. So compound A, which was the one that looks like this. Let's just draw it nice and small. CH2, CH2, CH. And then it had a Cl instead of the OH. And then CH3. That is what compound A was. And they're saying that that can be converted directly to the organic product in number 3. So they're saying that that can be directly converted into this bad boy over here. CH3, CH2, CH, CH, CH3. So that's an alkene. So we can go directly from a haloalkane to an alkene. Yes, we can. We've looked at that before. In that diagram, that reaction diagram I show you, haloalkane, alcohol, and then alkene, there's pathways going this way, there's pathways going this way and that way, there's pathways going that way, and reversible over there, and we can go from an alkane to an alkene, but we can also go from an alkene to a alkane. So we can most definitely go from a haloalkane to a alkene. It's going to be some type of elimination reaction. Now remember, when you're at a haloalkane, you can go to an alcohol or you can go to an alkene, and in both of those you can use base. Remember, you could use KOH and NaOH. But who can remember what determines whether we go elimination, which is very aggressive, or whether we just go substitution and we just become an alcohol. Well, that is where we use either concentrated base or dilute base. If you use concentrated, think of that as very aggressive, then you're going to go elimination, which is this one over here. And if you use dilute base, well, then you're just going to go to alcohol. So it says, besides heat, write down the reaction condition needed for this conversion. You would need to use a concentrated base, such as NaOH or KOH. And something you must actually say, NaOH and KOH are strong. So we must actually say it's a concentrated, strong base. That's important. Now it says, this last one, write down two terms that describe this type of reaction. Well, first of all, it's called a elimination reaction. But what are we eliminating? Well, if you go from here to here, you're definitely eliminating a halogen, and you'd also eliminate a hydrogen. So it's dehydrohalogenation. D, because it's elimination, you're eliminating a hydrogen, and you're eliminating a halogen. The reaction between excess dilute hydrochloric acid, okay, so that one's your excess, and sodium thiosulfate is used to investigate factors that influence reaction rate. The concentration of HCl used is 1 mole per decimeter. The same volume is used in each run. Okay, the time taken for the cross under the flask to become... Okay, so this is a reaction I've done in real life before. All that happens is they put these two chemicals together, and as the reaction progresses, it produces some type of precipitate, and eventually you won't be able to see the cross, and then they measure how long it takes for that to happen. The faster it happens, obviously the reaction is happening fast. The slower it happens, the reaction is happening slow. So that's all that's really happening here. Now it says the first question, define reaction rate. Multiple definitions for this one. You pretty much just want to say that it is the change in, now you could either say concentration, moles, volume, mass, and then you could say of either products, or you could use reactants per unit time. Okay, this next one says write down the independent. Independent is the thing that the human or the person who's designing the experiment is changing. Okay, so it says that in the reaction between excess is used to investigate. The concentration is 1. Okay, so they're not changing that. They're not changing the volume of HCl because that's staying constant. The time taken, they're not changing the time taken. That is the outcome. That is the dependent variable, but that's not what the person is changing. So what is the person changing? Well, it looks like, if you look here, they're changing the volume of Na2SO3. But then what I also notice is that they're changing the amount of water. So the total volume for those two is always 50. So you know what they're actually doing? They're actually trying to change this thing's concentration, because as they start lowering the amount of that, but then they add 10 moles of water or 10 centimeter cube of water, they're making it more dilute. So what they are changing, the person doing this experiment, they are changing the concentration of Na2S2O3. They are changing the concentration of that thing by manipulating the amount of water in the experiment. 5.3 says calculate the value of P. Now this is, I don't really like this question. It's a bit weird, but what you must understand is that as they lower the volume, you can see that they are increasing the amount of water. So naturally the concentration of Na2SO3 is going to go down. You know, if you add water to something, it becomes less strong, it doesn't taste as strong. Like if you're making Oros and you keep adding water, the concentration of Oros goes down. So let me show you how they got this value over here. Pretend we didn't know what that value was. Then if you have 50, and we know that if the volume is 50, the concentration was 0.13. Now, if the volume is 40, then obviously the concentration is going to be a little bit less. So we could say that what is 40 out of 50 multiplied by 0.13. And if you work that out, you get 0.10. So that is what they got there. So now we can just go and extend this a little bit further and say, okay, fine, if the volume is 30, then what is X? Well, what is 30 out of 50 multiplied by 0.13? And that'll give us 0.078. So 0.078 mole per decimeter minus 3. And I know that this sometimes confuses some of you, like, isn't this 3 decimals? It's weird. I know in the exams they say 2 decimals, but when your calculator gives you an ending or like a rounded, or not a rounded, but when the decimals in your calculator stop like this, then if you just go put all 3 of those, they still mark it correct. But if you wanted to round it to 0.08, that is also accepted. Okay, so let's move on. So when 0.21 grams of sulfur has formed, okay, in run 1, okay, so sulfur is this one over here. When that is formed in run 1, the cross became invisible. Calculate the reaction rate of sodium thiosulfate in grams per second. Very easy question, because we know that this is the reaction over here. And we know that we're not going to look at the excess, but we know that this one is the limiting, and we know that if they give us the grams of this one, we can convert that into moles. And once we have the moles of this one, we can see how many moles of this stuff reacted. And then we can convert that back to grams. And then we'll know how many grams of this reacted. And then we can get its reaction rate. Okay, so we're going to go get the moles of this one over here by using N equals to M over capital M. And it's going to be for sulfur. So we know that it was 0.21, and sulfur, if you look on your periodic table, is 32. And so if we work that out, you get 0.00. I'm not going to round off because it's not a final answer. But if you did, at the end, they give you a range that your answer has to be between, because they know some learners round off at different stages. They don't really have a hard and fast rule about this. Okay, so that is the moles of sulfur. So now we have the moles of sulfur. Let's just make sure this reaction is balanced. I know that there are numbers here, but sometimes it's still not balanced. So 2 and 2 of those. I'm just going to quickly go through this. Yeah, there's one S over there and one S over there. And then oxygen, there's 3. Oxygen, there's 3. Hydrogen, there is 2 and 2. Okay, so we are balanced. So we can see that the ratio of sulfur to sodium, what's this stuff? Thiosulfate is 1:1. So therefore, the moles of sodium, whatever, is also going to be 0.0065625. So then we can get its mass by using this formula again. Okay, so we can use that formula again, N equals to M over M, but now we know the moles. We know the moles of sodium thiosulfate as that. Now we need to go get its molecular mass from the periodic table. Okay, now from the periodic table, you would see that Na is 23, sulfur 32, and oxygen is 16. So if you had to go get the mass of this, you would get 158. You should get 158. Okay, then to just get mass by itself, you would end up getting 1. I'm not going to round off because it's not a final answer, so M is going to be 1. But as I said, if you do round off along the way, it is going to affect your answer, but I'll show you at the end what your answer is allowed to be between. Okay, and that's just going to be grams. Right, so now we have the mass of sodium thiosulfate that was reacted, and how many seconds did run 1 take? Run 1 took 20.4 seconds. So this is the amount of sodium thiosulfate that actually reacted. So that is the amount that you can use to work out the reaction rate. You don't need to know the initial and the final. You just need to know the change. But this is the change because this is the amount that was in the reaction. So that is the change. And so the reaction rate is then going to be that number divided by the amount of time in seconds, which is 20,4, and that gives Now it's a final answer. So now I would say 0.05, and the units of that would be, I'll give you what the answers are allowed to be now in grams per second. Okay, so the answers that you're allowed to get is anywhere between 0.048 and 0.08. Okay, those you can get anywhere between that. Right, now it says another investigation is performed at different temperatures. Sketch the Maxwell-Boltzmann curve for the reaction at 20 degrees. Is that the one that we've already done? And then label this as curve A. On the same set of axes, draw the curve that will be attained at 35 degrees and label that as B. Okay, no problem. So with the Maxwell-Boltzmann curve, then on your x-axis you have kinetic energy, and that is measured in joules. And then over here you've got number of particles on your y-axis, number of particles. Okay, so let's just do the one at 20 degrees. We know a typical Maxwell-Boltzmann does something like that. Okay, let's just label that A. Now, if you increase the temperature, what happens is that the kinetic energy of all the particles increases. So all of these points are going to shift to the right. Okay, so your graph is going to be shifted right. But for some reason, it also drops a little bit. So you're going to get something like that. So it's shifted more right. You can see the peak was over here. Now it's over here. But it also drops a little bit. And that I'm going to call B. And that's for 4 marks. That's nice. Sketch it. And then it says explain the effect of temperature on reaction rates in terms of the collision theory. Okay, so the good old collision theory, right? So we know that for a reaction to take place, you have to look at the collision theory. And that tells us that the molecules must collide. They must have enough energy. And they obviously have to collide with the correct orientation. Okay, so what happens if we have a container now? I'm going to take this away. And we increase the temperature. What happens to that? Well, let's say we've got this container. And you've got these molecules that are busy moving around. If you increase the temperature, those molecules are going to start moving around faster and faster and faster. Does that not mean that they are going to collide more often? Does it also not mean that they are going to have more energy, and so more of them will have enough energy to overcome the activation energy? So it's 2 factors that we need to consider here. That's why temperature is such a powerful thing that we can do to increase the reaction rate. Okay, so we can say that an increase in temperature, let's try write neat. An increase in temperature causes the molecules to move faster, leading to more effective, or let's just say leading to more collisions, which increases the chance of more effective collisions. Because not every collision is effective. They have to have the correct orientation, blah, blah, blah. But if you can make them collide more often, then obviously you increase the chance that there will be more effective collisions, which increases the chance of more effective collisions. Now, for a second point, an increase in temperature, or let's rather say, because now I also want to talk about the energy, the activation energy. So at a higher temperature, the molecules have more kinetic energy, which allows more molecules to be able to overcome the activation energy. And then lastly, just end that off and say the reaction rate, with an increase in temperature, the reaction rate increases. So you see how I addressed both of these. I first addressed the fact that if you can make the molecules move faster, they will collide more often. That is what we spoke about there. Then a second thing, we said that also, because the molecules now are at a higher temperature, they're going to have more kinetic energy, which means that more of them will now be able to overcome the activation energy. Because remember, the molecules can only react successfully if they have enough energy to overcome the activation energy. So temperature, you need to speak about both of those, and that is why temperature is such an important parameter, because it affects both of these scenarios. Consider the following hypothetical reaction reaching equilibrium in a 4 decimeter container at 150 degrees. The graph below shows the changes in the amount of reactants and products over time. Write down the meaning of the term reversible reaction. So it is a reaction which can take place in both directions. Okay, it can go in the forward direction and in the reverse, or like that, or however you want to do these symbols. You know, it can go forward and it can go in reverse. Okay, so this one says state Le Chatelier's principle. So let's quickly talk about Le Chatelier's principle. Le Chatelier's principle is the one that says if you have a system that is already at equilibrium and suddenly you change something such as concentration, pressure, temperature, then the system will react in such a way that it can oppose the change. Okay, so if you come along to a system that's at equilibrium and you increase the pressure, then the system is going to do whatever it needs to do so that it can eventually lower the pressure again. If you raise the temperature, the system's going to do whatever it needs to do so that it can eventually what did I say? Raise or lower the temperature? I can't remember. Let's say we raise the temperature, then the system will do whatever it needs to do to lower the temperature. Okay, so that's what Le Chatelier is, but let's get the definition for you. Okay, so here we have it at the bottom. When the equilibrium in a closed system is disturbed, so if someone changes the pressure, concentration, or temperature, the system will then reinstate a new equilibrium by favoring the reaction that will cancel or try to oppose that disturbance. Okay, now, so we've done this question. Now it says a change was made at 80 seconds, which is over here. Okay, a change was made. Where's the mark allocation here? Sorry, I'll get that for us now. This one is worth. This one here is worth 1 mark. So let me put here a 1. Okay, so it says write down the change that was made at 80 seconds. So let's have a look. What we see is that, so we've got these 3 components. If you look at AB, it's this dotted line. So with AB, we can see that it's just this dotted line over here. And at 80 seconds, nothing happens. It doesn't spike up or spike down. It just gradually changes after the 80 seconds. If we look at B2, B2 is this line over here. We can see that it goes like this. At 80 seconds, it doesn't do anything drastic. It doesn't spike up or spike down. It just gradually goes down after 80 seconds. Okay? But if we look at A2, A2 is the solid line. If you see at 80 seconds, it has a drastic spike. And so what they have done is they've increased the amount of A2. So maybe they added some A2 into the container. Maybe they opened the container, quickly added in some more A2. Because we see here that this is number of moles. So we can just say more A2 was added to the system. You can also say the concentration of A2 was increased. That's also valid. Okay, now it says use Le Chatelier's principle to explain how the system reacts to this change. Okay, now this is important. Some learners get this a bit confused. So remember, the change that was made by the human was here at 80 seconds. This is where the change happened. This is where something drastic happened, like we open the container, we add more A2. Now remember, what Le Chatelier says is the following. Remember that this system was already in equilibrium. You can see these lines were already in equilibrium. So when equilibrium is disturbed, where did we disturb it? There. What will the system do? The system will try to achieve a new equilibrium. Have a look over here. How? By favoring the reaction that will somehow try to cancel or oppose the disturbance. And so here we are at equilibrium. And then here we are at equilibrium, but in between is when someone made a change to the system, and then the system gets a little bit unhappy and tries to fix it by doing something that will try to get back to a new equilibrium. Okay, so all you need to do is you first need to mention what happened. Okay, so more A2 was added to the system. This is usually a 4-mark question. Next, what is the system going to do? So the system will always try to do the exact opposite. So the system will try to decrease the amount of A2. You see, more A2 was added, so what's the system going to do? It's going to try to decrease the amount of A2. It'll always try to oppose or go against what was done. How will it do that? So now, we come up to this reaction over here, and we see which of these reactions, either if it goes in the forward direction, or if it goes in the reverse direction, which one is going to make the A2 begin to go down? Well, that would be if you go in the reverse direction, because then A2 is seen as a reactant and not a product. But if you go this way, then A2 is a product and not a reactant. So we're going to go in the reverse reaction. So we're going to say reverse reaction is favored. Now, if the reverse reaction is favored, what will happen to the amount of A2? It will begin to go down. So have a look here. Oh, it begins to go down. What will happen to the amount of B2? It'll begin to go down. Look at that. What will happen to the amount of AB? It should begin to go up. Oh, look at that. You see, this stuff is amazing. It makes perfect sense. And so this is, by the way, what you would say for 6.3.2. This question for 4 marks says, calculate the equilibrium constant at 120 seconds. Okay, 6.4. Calculate the equilibrium constant at 120 seconds. Okay, so that's going to be over here. And so we don't need to use a Kc table because we can read off all the values. We can see the moles at equilibrium and all of that. So we must know, though, that Kc is equal to your products concentrations over the over the concentration of your reactants. And we have to look at this equation. So we know that these are the products. So A2, concentration of A2, and then concentration of B2. Remember, we only use gas and aqueous in a Kc calculation. We don't use solids and liquids. So if any of these said solid or liquid, we wouldn't include them in the Kc. You would just leave them out. Now we got concentration of AB. Now we must remember, though, that you see in the front here, there's a 2. That becomes the exponent in this expression. Now remember, these square brackets mean concentration. So C equals to N over V. We know the volume of the container, and we can just read off the moles of each substance. So for A2, that's this one, at that time has 8 moles. So we're going to say C equals to N over V, so it's 8 over 4. Then for B2, it has 2 moles, so 2 over 4. And then AB is 10 moles, so 10 over 4, but to the power of 2. Okay, so go ahead, type it all in. And we should get 0.16. So where do we write that? 0.16. This one says at T equals to 130. Okay, so at T equals to 130, the temperature is decreased to 100 because remember it was at 150. Okay, so they decrease the temperature. First question, draw a potential energy diagram. Now that is not a very common thing for them to ask, so I can imagine that the learners that wrote this exam might have felt a little unsettled about this. Now, some of you might even be like, Kevin, what is a potential energy diagram? Well, it's that thing that looks like this. It's got 2 different types. It's got 2 different formats. It could either go like that, or it could go like that, where it starts lower over here, or it starts higher. This is called endothermic, and this would be if it is exothermic. Now we don't know what it is. They haven't given us a nice little symbol over here that does something like that, or that does something like that. But we can figure it out by looking at the fact that we know the temperature has been decreased at 130 seconds. We can then look and see how does the system react, and from that information we can work our way back and figure out, is this an exothermic system or an endothermic system for the forward reaction. Okay, we're always looking at the forward reaction when we write this part down. Okay, and when we draw it like this, we're going to look from the perspective of the forward reaction. So let's try to understand this. Okay, so we know that the temperature was dropped. We can easily all understand that. Okay, so let's write that down for ourselves. Temperature was decreased. So immediately, remember, we were at equilibrium already, and then what did we do? we decreased the temperature. Maybe we threw in a whole bunch of ice, or maybe we did something, but we decreased the temperature. So what does Le Chatelier say? When equilibrium is disturbed, as it was, the system will try to oppose it. So what's the system going to try to do? Of course, it's going to try to increase the temperature. So system will try to increase the temperature. How does a system increase a temperature? A system increases a temperature by going exothermic, because exothermic releases a lot of heat into the environment. So we can say that the exothermic reaction will be favored. Exothermic reaction will be favored. Okay, so we know that exothermic will be favored. So now what we do is we come here and we see which reaction was favored. Well, what we can see is that the amount of AB goes up. So this one goes up and the other two go down. So it means that the reverse reaction must be favored, because this is now being a product because more of it is being produced, and these two are reactants because they're becoming less. So we can see that the reverse reaction is favored. So we can say here, reverse reaction was favored. By the way, we're not going to get any marks for this part of here. This is just for our own reasoning, that you could maybe just write it out on the side of a page or whatever, just to help you to verbally or to try reason your way through this. If you're very good with this section, you can do this in your head. But for some of us, it just helps to just write it down like this. Reverse reaction was favored. Now you just draw a conclusion. Exothermic will be favored. Reverse was favored. What does that mean? Therefore, reverse is exothermic. Reverse is exothermic. So what does that then mean for the forward reaction? Well, therefore, the forward is the exact opposite. The forward is endothermic. So now we just need to know the different shapes of our potential diagrams, and we should know that endothermic is when you go like that, where you start low, end high. Now, of course, we need labels on the axes. So this one here is typically called time. Some learners also call this course of reaction. That's also accepted. And then this on this one, remember it's called a potential energy diagram. So this is the potential energy. So we just put that on our y-axis. Potential energy. That's measured in joules. Time measured in seconds. This one over here says, will the equilibrium constant at 100 be greater, less than, or equal to Kc at 150? So remember that temperature is the only thing that can change Kc. So Kc will definitely change. So it's a very easy question, because all we need to remember is that Kc is you could go calculate Kc all over again if you really wanted to, but it's not necessary. We know that Kc is products over reactants. Now, we said that the reverse reaction is going to be favored. So as you go in the reverse direction, what happens to the amount of this? Well, this is going to start to increase. So these particles at the bottom here, they're going to increase. And then the amount of this is going to go down. So mathematically, if your numerator becomes smaller and your denominator becomes bigger, then this overall number actually becomes less. So we can say, will the thing at 100, it will be less than. And then we can just say reverse reaction was favored. And that's it. They will, they give you 1 mark there, and then they gave you 2 marks for this one over here, for that statement over there. Okay, I just want to make sure we've done everything. So I know we've still got 1 more question to do, but we did do this one, write down that yes. Okay, the initial reaction now takes place in the presence of a catalyst at 150. Okay, describe the changes that will be observed on the graph between 0 and 60. Okay, so they're coming back to this part over here. If you use a catalyst, the catalyst just makes the reaction happen faster. So all that would happen is we would still reach the same equilibrium position. Why? Because only temperature can affect your Kc. So the Kc would have to be the same. So these values would all have to be at the same point. All that would happen is that the graph, the drops would happen much faster. So maybe to there. And you would reach equilibrium much sooner. And these would go up to there. And then you see we reach equilibrium from this position instead of reaching equilibrium from this position where they become parallel. They would become parallel much earlier. You see that? That because a catalyst makes the reaction happen faster. So, the initial reaction now takes place in the presence of, describe the changes that will be observed on the graph. So we can just say that the gradients of the curves will be steeper and equilibrium will be reached sooner, or let's say earlier. But we must say that the equilibrium values, which is, for example, the 6 and the 4, will still be the same. Will still be the same. To identify metal M in an unknown metal carbonate, the following procedure is carried out. Step 1, that amount of grams of impure MCO3 is reacted with that. Okay, the excess that is then neutralized with that. Boom. And assume the volumes are additive. Don't worry too much about that. It doesn't really mean anything. The following reactions take place. Okay, so this is in step 1. This is in step 2. Right. Define the term strong base. So we know that acids, they typically like to ionize. Bases typically like to dissociate. If something is strong, if it's a strong acid, it ionizes completely in water. If it's a strong base, it dissociates completely in water. So we can say that it is a substance that dissociates completely in water. Okay, now 7.2. Calculate the number of moles of barium hydroxide that reacted with the excess HNO3. Okay, well, it's easy. They've given us all the information over there for barium hydroxide, and so we're just going to use C equals to N over V, and we're going to get the moles by itself, so N equals to C times V, and so that's going to be concentration of 0.15. Remember to convert your centimeters into decimeters. It'll be 0.02. How did I do that? I divided by 1,000. And this will give us 0.003 moles. Okay, so we need to calculate the pH after step 1. Right, let's try to figure this out, shall we? So we know that in step 1, we've got impure. Don't use this at all. Don't even worry about that. Whenever something's impure, you cannot use that information at this moment because, yeah, you just leave that alone completely. But we know that we have MCO3 in here and nitric acid, or let's say HNO3, which is nitric acid. And we know that this one is the excess. How do I know that? I'm guessing. No, I'm joking. It says here, the excess HNO3, meaning that it's the excess from this question, okay? They're going to take that excess, right? Yeah, let's just remember that, the excess. Now, whatever is the excess, let's write that a bit better, sorry. So the excess is then going to be taken to step 2. And there we are going to react the excess HNO3 with barium hydroxide. Okay, so the idea is, guys, what we are going to do is we are going to use this information here, because you see how we know how much barium hydroxide we have. We know exactly how many moles of this we have. So that means from the balanced equation over here, we can work out using mole ratios how much HNO3 must have been over here, and then we know that that HNO3 is the amount of excess that we had left over after this reaction. And that is going to help us to work out the pH after step 1 reaction has taken place. Let me explain that again. We're going to take this part over here because we know it's moles. We can then easily just use the balanced equation to work out how many moles of HNO3 there are. And we know that that is actually the amount of excess that we had from this previous reaction. And so if we know how much excess we have inside here, then we know how much HNO3 is floating around after this reaction took place, because they said after step 1, and then we can do pH calculations like that. Does that make sense? So let's go that awkward moment when I ask a question knowing that no one has the ability to answer me in live, like in person right now. So yeah, I hope it makes sense. Right, so what we're going to do is we already know the moles of barium hydroxide. So now we're just going to look at the ratio of barium hydroxide to HNO3 in this reaction. Okay, and we can see that the ratio is 2 of these for every 1 of these. So if we have 0.003, then what would this be? It would have to be 0.006. Okay, fantastic. So we can then say that the moles of HNO3 in step 2 is 0.006 moles. Okay, but now that is also the excess that we had over here. So we can now say that in this reaction, the excess, not the amount that reacted, the excess, the leftovers, is 0.006. So you can imagine that these two things reacted, and after all of this was neutralized, there was 0.006 HNO3 left over floating around in the container. Now, what does leftover acid do in a container? It reacts with water because we know that acids like to ionize. And so you're going to form H3O plus NO3 minus. Make sure it's balanced. It is. Okay, so we know how much excess HNO3 there is. It's 0.006. So we know how much of this is going to form. We know that H3O is also going to be 0.006 moles. And we know the volume of this container. It's 25. Now, some learners are going to say, no, it's not. How can you just look at the mass? How can you just look at the volume of the nitric acid? What about the MCO3? Doesn't it have volume as well? But it's not a liquid. Look at the equation. It's a solid. So it's dissolved in the solution, so it doesn't contribute to the volume of the solution. Ah, Kevin. Haha. So we have the volume of this container. So why is that important? Because we know that pH is equal to the negative log of H3O plus. And so if we can then use C equals to N over V, we can get the concentration of H3O plus. In fact, we can actually just do it in the equation itself because we know the moles and the volume is 25. So we say 0.025. So this is the concentration of H3O plus, and that'll give us, and if we round that to 2 decimal places, we get 0.62. Okay, now the one that you've been avoiding, 8 marks. Okay, it's going to be okay. So let's try to understand. Let's clear up some space first. To be honest, I don't know why it's 8 marks. There's actually a pretty straightforward way we're going to do this. Check this out. In step 1, we know how much nitric acid we were given in the very beginning, but we know that a lot of that was in excess. But look at this. We can take that nitric acid that was originally placed in this container, and we can work out its moles, which is 0.4 multiplied by 0.025. Remember to convert to decimeters. If in doubt, use decimeters. And that's going to give us 0.01 moles. Check this out, guys. That means that we originally started with 0.01 moles of HNO3. How much was left over at the end? Remember, this was the excess. So then you can then think about this. How much HNO3 did we actually use in this reaction over here? Well, we started with 0.01. We ended with this amount left over, so we can minus those two. So the moles of HNO3 used, or let's say reacted, in step 1 would then be 0.01 minus 0.006, and that gives us 0.004. So now we know the moles of HNO3 over here. We know how many moles were used. So then we can use mole ratios to then work out what this one's moles would be. Okay, So I think this is going to get us somewhere. Let's have a look. So we know then that the ratio of HNO3 to MCO3 is 2 to 1. So if this is 0.004, then this must be 0.002. Okay, so we have the moles of MCO3. Don't use this value over here together with that, because this is not an impure number. I mean, this is not a pure number. This is an impure number. So you don't actually know how much of it is MCO3 because it's impure. But they've given us the percentage purity. So we've got something we can do now. We know that percentage purity is equal to the amount of pure stuff divided by the amount of impure stuff, and then times 100, because it's a percentage. So we could say that 85, which is the percentage, is equal to the pure stuff, which is what we're going to figure out, divided by the impure, which is 0.198, right, times 100. Okay, so I'm going to divide the 100 on the left, so you get 0.85, then going to take the 0.198 over, and we should end up with don't round off, it's not a final answer, 0.1683 grams. So now we know, how many, I see why it's 8 marks, my goodness. Okay, so we now have the pure MCO3 mass. Okay, and now I'm at a point where I'm really thinking hard of like where to go from here. So we've got the mass, but now we need to try think about how are we going to identify metal M? Like, are we going to have to do like some type of, what's that word called? What's it called? Empirical formula or something like that. Never mind being silly. What we can do is we know, where did we write that down? We know the moles and we know the mass. So we can use this formula and we can calculate what its actual, by the way, this M is not that M. Hate it when teachers do this because it can cause some confusion. This M is the molar mass from the periodic table. So we've got the moles and we've got the mass. And so moles is going to be 0.002. The mass is 0.1683. And there we go. Okay, now to get M, you would take it to that side, and then you would end up dividing, you would end up getting something like 0.1683 divided by 0.002, and that's going to give 84.15. But that's not this M. That's not that M. Shame. Learners that are struggling in a test and they're panicking, they're going to be like, yes, I got M. But it's not the same. Grams per mole. Okay, so we now know that this entire thing has a mass on the periodic table of 84.15. So we could now say 84.15 minus carbon minus 3 oxygens. I'm getting these masses from the periodic table. And if you work this out, you get 24.15. So that is what M would be on the periodic table. So now we need to go to the periodic table and find a metal that has a mass of around about 24.15. And so that is going to be magnesium. Of course, it's not going to be exact because of rounding and stuff, but 24.15 is close enough. And so the answer for that question is magnesium. And so there we have completed what I feel is a very good question. Very, very, very good. Very challenging as well. But yeah, I think it was quite a good one. A cleaned copper strip is placed in a beaker containing silver nitrate solution at 25 degrees. After a while, it is observed that the solution becomes blue. Okay. Write down one other observable change besides the solution turning blue. Okay, so let me try to explain why the solution would turn blue, and let's try to figure out what's going on here. So remember, I've made some of those videos where we put two things together, a certain solid and a certain liquid, and we ask ourselves, will a reaction take place? You know, like for example, your teacher might have mentioned in class, if you're storing like a nail inside a certain solution, some solutions will work better than others because some solutions will cause a reaction, whereas others won't. That's what's going on here. Okay, so let's try to figure this out. We know that AgNO3 is actually broken up as Ag plus and NO3 minus. If you don't, I know this is feeling pretty awkward right now. Trust me, it does though. It does break up into those ions over there. It's very soluble. And then the copper strip is pure copper. So if we go look at our table, now remember I like to use table 4b, whereas some learners use table 4a. Okay, now I don't know how you like to interpret your tables, but I've gone and I've just pulled out a part of this table. But you got to always circle what you have. So what do we have here? We've got copper. Now there's multiple coppers, but we don't really use the one with this one. We use the one that has the 2+. Okay, so but I'm not going to circle the whole reaction like I would if this was a galvanic cell. This is not a galvanic cell. This is an electrolytic kind of process. So you only circle what you have. And what do we have on this side? We have Ag+. So I'm not going to circle that. No, I circle what I have. Now, I've taught you guys, when you look at these tables, that if you ever have a situation where you've got something on the left-hand side that is lower down than the thing that is on the right-hand side, then a reaction will naturally or spontaneously take place. If you're not sure about it, let's pretend that a reaction does take place. So then what would happen? If a reaction does take place, what would happen here? Well, it can't go that way. Why? You don't have any silver to start with. It can only go this way because you only have that. And if a reaction had to happen over here, it won't go this way because you don't have any of this. It can only go that way. So let's pretend a reaction does take place, okay? Then let's see if this will happen naturally by itself or do we need a battery? So we know that the formula for EMF goes like this. Now we should know that the cathode is always the place where we have reduction and the anode is always the place where we have oxidation. That is no matter whether we are dealing with a galvanic or electrolytic. It doesn't matter. Now you should also know that when a reaction is written like this, in that direction, when the electrons are on the left like this, we know that that is reduction. And then when it's written like this, that is oxidation. So then we can go fill in the formula. The reduction value is 0.8. The anode value is 0.34. And if you work this out, none of this is for marks, by the way. I'm just busy explaining to you what is actually happening in this question so that you can have a much more comfortable idea of what is actually going on. 0.46. What that tells us is that this reaction will happen automatically by itself. There does not need to be any battery supply, nothing. It will happen. So you would not be very wise if you wanted to have some type of copper nail. Let's say this is your nail because you are a builder, for example. You would not want to put your copper nail inside a silver nitrate solution because a reaction is going to happen. And what would then take place is that this copper, which is pure copper, is going to slowly but surely convert into copper ions. That is what gives the blue color. Copper ions have a beautiful blue color. You can tell I've been doing this for too long. Who the hell says that it's a beautiful, beautiful blue copper ions? No, but they are beautiful. If you've ever seen that typical lovely blue solution your teacher might have shown you in class, that is copper ions. So we know that the copper is going to be converted into copper ions, and so what's going to happen is you're going to get these copper ions now floating around in the solution. That's the beautiful blue, as I said. And then what happens is that the Ag pluses that were originally in the solution are going to convert into pure silver, and you are going to start getting some pure silver on the surface of this strip. And so you're going to start seeing a layer of silver deposit forming over there. So what other observable change would we see besides the blue? Well, we would see a silver deposit forming on the strip. Okay, nice, guys. Okay, now it says, what is the name or formula of the oxidizing agent? The oxidizing agent is the one that is reduced. So which of these is being reduced? Well, here's the reduction reaction. So which substance is being reduced? Is it this one? No, that's the product. This is the thing that is reduced to become the product. So the name is going to be silver ion, or you could just say Ag+. And you got to be so specific. If you just say Ag, wrong. There is a huge difference between Ag and Ag+. The one is like in the solution as an ion, and the other one is the pure silver. And you got to distinguish between the two. You don't want to just say, oh, it's copper, or oh, it's silver. You got to know, is it the copper ion? Is it the silver ion? Is it the pure silver? All right. Okay, this last question now says, explain the answer to 8.1.1 by referring to the relative strengths. They're pretty much just asking us, why is a reaction taking place? Now, this is that part where you can say the one is a stronger oxidizing agent than that one, and blah, 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 blah. But there's so many different ways. So let's go through a couple options. So you could say that, for example, I'm just going to choose this one, and I see on the arrow here that it's an increasing oxidizing agent. So all I would say is that Ag plus is a stronger oxidizing agent than the other one that it could have been, which would be this one. It must be on the same side of the table. And will be able to oxidize copper to become Cu2+. Let me explain. We are saying that this one is a stronger oxidizing agent than this one, and will therefore be able to oxidize this copper to become Cu2+. It shouldn't surprise you. Ag plus is a strong oxidizing agent, so it is able to oxidize other things. So it can oxidize Cu to become Cu2+. Okay, that's one option. Your other way you could have written this, you only have to choose one of these, but you could have done it the other way around. You could have spoken about this one compared with this one. So you could have instead looked at this arrow, and you see that it's increasing reducing agent. So you could say that copper is a stronger reducing agent than the other one on that side of the table, which is Ag, and will be able to reduce Ag plus to become Ag. You should see the similarity, or not the similarities, but it's a pattern. It's a pattern over here. So try to make sure that you understand that. In the test, you only have to choose one or two. It doesn't really matter. And then sometimes in a test, they would also allow you to do the calculation that we did, where we showed that the EMF was a positive value, meaning it's spontaneous. But that's only if they say show by calculation or something like that. Okay, so there we go. Hope that makes sense. A galvanic cell is now set up using copper and silver strips as electrodes. A simplified diagram is shown below. Okay, so here we have a galvanic cell. Now they say, and it's with copper and silver. So this is obviously silver plus. Now the way you misunderstand it is that there's silver plus, so the solid part is silver. And then they said this is copper. Now the copper we use is always going to be the one with 2+ and pure copper. So here we have pure copper, and then in the liquid you would have some type of aqueous like that. Now it says write down the name or formula of electrode A. Well, that's just going to be, you could say silver or Ag. Don't say Ag+. It's specifically the solid metal part. Okay, now it says what is solution B? Now you must specifically say Cu2+ or copper ion, but don't say copper. Okay, it's a very, because here they want the solution, here they want the electrode. It's very specific. Now it says what is the overall net equation? This is very easy. So we know that this is our galvanic cell, so we circle the two reactions that we have. This is table 4b, by the way. I use table 4b. Most learners do, but some do use A. Now what I do is I follow the arrows, and I see that the lowest one, the arrow is the one on the left, so I circle that one. And then I look at the arrows on the right hand side, and I see that the highest one is over here. So I know then that this reaction is naturally going to go in this direction, and this one is naturally going to go in this direction. And this is the process we use when we're doing galvanic cells. Okay, we look at which things are going to what's going to happen spontaneously. So we follow the arrows. That helps us to see what will happen spontaneously. So I know that the first reaction is going to be, or one of the reactions is going to be that over there, and then this one is written with the copper first. So I start with the copper, and then that becomes, or let's put the arrow here, that becomes copper 2+ plus 2 electrons. And so now if we want to balance this, we need to realize that the electrons have to be the same. So here we've got 1, but here we've got 2. So I'm going to multiply this entire reaction with 2. So I'm going to put a 2 there, a 2 there, and a 2 there. Now we can simply plus these two reactions together, and so it ends up becoming 2Ag plus its 2 electrons plus copper, and then on the right hand side of the arrow we've got 2Ag plus copper 2 plus 2 electrons. Now the electrons cancel, and that's the point of getting them the same, and so that is our balanced equation for 3 marks. Says that the salt bridge, here it is over here, contains potassium nitrate. They often like to use potassium nitrate. Okay. In the salt bridge, write down the formula of write down the formula of the ion in the salt bridge that will move into the silver solution. Okay. Choose from this one or this one. Very easy. So, if you look at what happens at this reaction over here, if you look here, we are going from Ag plus and we are converting it into Ag. So what are we doing with the amount of this positive ion over time? Are we making it more or less? Well, it's less because you're using it to create Ag. So the amount of positive ion in this solution is going to start decreasing. So that becomes a bit of a problem. So what will happen is that this positive potassium would then move over to make sure that this solution remains as positive as possible. So it's going to be the K plus. Okay, and now choose a reason for the answer. Let's just say from the reaction Ag plus gives you Ag. The Ag plus will become less. So then K plus will move into the solution to maintain electrical neutrality. Okay, and for those of you that are curious, yes, the NO3 minus would end up going over there. Why? Because in that system, you've got copper turning into copper 2 plus 2 electrons. So the amount of positive ions are becoming more and more and more. So it's going to cause an imbalance. So the negative ion makes its way into that solution to try to lower that positivity and keep it neutral. An electrolytic cell was used or set up to purify a piece of copper that contains silver and zinc as impurities. Okay, so you've got in this thing over here, you've got copper, you've got silver, and you've got zinc. Okay, and the goal, and that's why it's called impure, because you've got these other things. Now the goal of this question would be to get this copper out of this and over to this side over here where you can deposit the pure copper over there. Okay, so a simplified diagram, electrode R is impure copper, of course. So it says, define the term electrolysis. Electrolysis is a chemical process that converts electrical energy, like a battery. We do need a battery when we're doing electrolytic processes, to chemical energy. Okay, write down the reaction that will take place at electrode Q. So we need to understand the whole story here. So in this solid, we've got pure copper, pure silver, and pure zinc. Not ions, the actual metal. So what we must realize is that to be able to get this there, you have to first convert this thing back into an ion, because that is the only way it can travel. It can't travel as a metal. If it's a metal, it's just going to fall to the floor. You got to convert it into an ion, because ions can travel through liquids. So once you've done that, we'll talk about how we're going to do that, but you're going to convert it into an ion. That ion is then going to make its way over to this side over here, and then it's going to be reduced back to become a pure metal again. So that's quite cool. You take it from a metal, you convert it to an ion, the ion is then able to travel over, and then you reduce it back down to a solid again. Let me show you the table 4b. So the reaction that we typically use in grade 12 is this one here with the 2 plus and the 2. So when you're converting it from an ion back down to a metal, you write it like this. You don't want to write it the other way. At this electrode, you're not converting the copper to an ion. That's what's happening over here. Okay. Now, in which direction do the electrons flow in the external circuit? Choose from Q to R or R to Q. I don't want you to memorize this kind of stuff. I want you to have a very firm idea of how this works. So if you look carefully, at this electrode over here, you've got this copper 2+ that's on its way, and it undergoes this reaction. So it says that you need a copper 2+, and then what do you need? You need 2 electrons. Where do those electrons come from? Well, those electrons would come from the power source. So the direction is going, the electrons are going to go towards Q. So from R towards Q. So we're going to say R to Q. Okay? Where do the electrons come from over here? Well, think about, let's say, for example, when we oxidize the copper, then the reaction is going to be written in the opposite direction. So then its copper turns into copper 2+ plus 2 electrons. So now you can see that the electrons are part of the products, so they get given off and then they go back through the battery like that. Okay, so it's going to be R to Q. The electrons are going to go like that. This one says, calculate the current that you would need to form 16 grams of copper. Okay, so where are we going to form copper? We're going to form copper over here. So you are going to use this reaction as your guide. So, okay, let me explain these questions. These questions are all about IQT. So you know that formula I equals to charge over T. So your goal is the following. You could use this information, which is the copper, and you could convert that into moles. Once you have that, you can convert it into, you could work out the ratio of electron moles. And if you know how many electron moles you have, you can work out how many electrons you have. And if you know how many electrons you have, you also know how much charge you have, because you know what the charge of an electron is. It's that 1.6 times 10 to the minus 19 number. And then all of a sudden you have the amount of electron charge, and you've got the time, and then you get current. It's actually very straightforward. Let me explain that again. You're going to work out the moles of copper. You then use the mole ratio in this equation to get the moles of electrons. You can then use Avogadro's number to work out how many electrons that is. Then because you know how much the charge of one electron is, 1.6 times 10 to the minus 19, you could work out the total charge, and then you've got charge, and then you've got time, and then you get current. Straightforward, right? So step 1, we need to go work out the moles of copper. So we just use N equals to M over capital M, and that's going to be 16 divided by copper's mass on the periodic table. Let's go get that quick. Okay, so I went and saw that copper has a mass of 63.5. Guys, specifically I'm talking to the guys right now. If you're in the exam and you want to like pick up a chick or whatever, like while she's writing her exam, you know, it could be a good idea to try to do that, because in that moment she's a bit panicked and stuff, and so her guard is maybe a little bit down, and she's a bit flustered, and so you could literally swoop in there and get yourself a date very quickly. All you do, now trust me, you got to use this carefully because it works really well. Even the invigilator, one of those old tannies, she might even fall for this one. She might be like, "O Jana, dis mooi." So check, what you're going to do is you're just going to glance over to this girl sitting there and just be like, because obviously she's doing this question as well, so she knows it's all about copper. So you can just look at her and be like, "Hey, I see you. Get it? I see you. Trust me, guys. That guy ain't going home alone tonight." All right, so we need to calculate the number of moles, and so that's going to be 16 over 63.5. Busy sitting in my dressing gown right now. Yeah, random. Okay, so that's 0.25. I know it's not a final answer, but if you round off, you know, they give you a range that your answer is allowed to be in. But if you want to keep a few decimals, that's fine. Maybe let's do that. Let's keep, I'm just going to write down the first 5 decimals like that. I'm not going to round off the decimals. I'm just going to keep the first 5 decimals. Okay, so that is now the moles of copper. Now, if you look at the moles of copper to the moles of electrons, it's 1 to 2. So the moles of electrons would then be double that number. So I'm just going to times that number by 2. Times 2. That'll be 0.50392. Okay, now that we have the moles of electron, we can use Avogadro's number to see how many electrons there are. So Avogadro's number is this one over here, which we don't use too often. But yeah, so we have the moles and we have Avogadro's number. It's that constant on the formula sheet, 6.02 times 10 to the 23. So we could then say 0.50392 multiplied by 6.02 times 10 to the 23. Okay, type that all in, and we get 3.0, I'm just going to say 335 times 10 to the 23. So that is the amount of electrons that we now have. So think about it. That is how many electrons you have flowing through. And every electron that flows has a certain charge. What is the charge of an electron? The charge of an electron is negative 1.6 times 10 to the negative 19. So if you have a whole bunch of electrons coming past, how would you work out the total charge? You would just multiply these two numbers. Easy. You know how many electrons are going past. You know what the charge of an electron is. And so, yeah, let me use this formula over here. And so now this n is not moles. This n is the number of electrons. So that's going to be 3.0335 times 10 to the 23. I'm then going to multiply by this number. But I'm not going to put a negative because I'm just trying to work out the total charge. I'm not interested in if the charge is negative or positive. That doesn't affect the current. So I'm just going to leave it as a positive. If you do put it as a negative, they don't really mark you down on that. I've seen that on the memos. Okay, now if you had to go work that out. Oh, geez, how does it just come up with such a beautiful number? 48. Oh, it usually does that. 536 with these types of questions. And that's going to be Coulomb. Now we have the amount of charge. And now we can just get the current. So it's going to be 48536. Now the time is 5 hours, but it must be in seconds. Now I know some of you are like, ooh, geez, how do we convert that? So you're first going to convert it into minutes. And then that's 300 minutes. And then that you can convert into seconds, which would be 18,000 seconds. Okay, so 18,000 seconds. All right. And then if we had to go work this out, 2.70 amps. It's another one you could do, guys. Glance over at her and be like, hey, what are you doing for the weekend? And then she's going to be like, dude, I'm writing an exam. And then just be like, I'm taking you out on a date. By the way, I'm super amped. You guys think I do this chemistry stuff in order to help you. Pfft. I'm working on my own game here, guys. That's what I do. You know how many girls I pick up by talking like this to them? I literally walk into a bar and I just start whipping out these jokes. And it's just so easy. It's just getting so boring now, to be honest. Okay, that was also a joke. I found this crazy. I went and looked on the memo to see what answers you are allowed. You can actually have all the way from 1.34, all the way from 1.34, all the way to 2.70. It's like, what? Just put any number. Put anything you like. Probably going to get it right. I mean, that's crazy. But obviously, they're going to look at your method and all of that stuff. I was just looking at all this writing all over the screen. I know it's pretty messy, but obviously as you follow along with me, you see where I'm at. But yeah, I can just picture like seeing like a TikTok meme about this. And then, you know, you get those TikToks and then people put voiceovers on. It'll be something like, trying to understand math when Kevin Math writes all over the screen. I don't know. I don't know if I got the accent right, but some of those voiceovers are so bad. The other night I heard... trying to study with Kevin Math Seance. Okay, let's carry on. During this electrolysis, only copper and zinc are oxidized. Give a reason why the silver is not oxidized. Oh, that's a good question. But look, this was the last question from this exam paper. So at this point, if you just want to lass it, go chat to that chick rather. If she's left the exam building, dude, get out of there. What are you doing sitting here waiting, nerd? No, I'm joking. You should obviously always try to get your marks. Okay, so it's very important, this one. So we know that in this metal over here, there was copper. What else did they say? Zinc and silver. Now, there's a battery here. Now, that battery... we know that it definitely has to be strong enough to oxidize copper, because otherwise this would be an awkward question. The scientists would set it up and they would just sit there and be like, so, John, how's your PhD paper coming along? There would be nothing happening over here, so they wouldn't really have much to talk about. So we got to be careful. This battery, if we make the battery too strong, it might oxidize more than what we want. Okay? So what they said is that only copper and zinc are oxidized. So this one was oxidized and this one was oxidized. But the silver wasn't. So the battery was obviously strong enough to oxidize these two, but it wasn't strong enough to oxidize this one. Okay, so I'm going to have to explain it from the table, but at the moment I don't have zinc on here, so I'm just going to modify things a bit. Okay, so let's try to... Oh, that's awkward. I still don't have zinc. Hold on, I'll be back now. Okay, I'm back. So we have zinc. We have the copper 2 plus reaction. Now, there's a lot of coppers on this table, but you've got to be specific. It's not this one. It's this one here that we use. And then we've got silver down there. Okay, so if you are the person doing this experiment, what you would do is you would look at this voltage over here, and that's typically what you would make your battery voltage. Fantastic. What that means, however, is that this battery is going to be strong enough to cause copper to be able to oxidize. But it's also going to be able to oxidize any of these ones above, because this one only needs 0.17 volts, this one only needs 0.16. These ones are negative, meaning that they are so desperately wanting to oxidize, they will do it for free. You don't even have to give them a battery, they'll just oxidize. So everything above, everything from 0.34 and above, they are all going to oxidize. Every single one of those will be oxidized by a battery of that strength. Anything below will not be able to be oxidized. That is why the silver is not being oxidized. It would need a battery of 0.8 volts. So all of these are going to oxidize. Okay? And so that is why they said zinc will oxidize. So why? Well, just use this. Just say copper and zinc are, and then just look here, stronger reducing agents than silver. So you can literally just say that the potential difference, which is the power source, is not strong enough to oxidize silver. Okay, you can also say, you can use this arrow here, and you can also say that zinc and copper, this one, zinc and copper are stronger reducing agents than silver and will be oxidized, while Ag will not be oxidized. But I think this one's more easy to understand. Okay, and so I just want to come back quickly. I know that some of you might be thinking, for those of you that haven't been thinking about anything beyond what we've spoken about, we're done now. But for those of you that maybe think, okay, but if the zinc is also being oxidized, then is that not a problem that we've got zinc 2 plus and copper 2 plus? Because they are naturally both going to be attracted to this terminal, which would be negative. So then why is it that the zinc doesn't get reduced, but the copper does? Well, that's just based on, if you look on the table, and if we look at the copper 2 plus, oh, I don't have zinc again. I'll be back now. Okay, so if we look on the table, we can see zinc 2 plus is up here, and copper 2 plus is down here. Sorry, it's a bit weird there, squeezed there. But if you look at the oxidizing strength, we can see that as you go down on the left, this one is much stronger. And so even though we've got zinc 2 plus that is now oxidized, it is the copper 2 plus that would preferentially be chosen, or it would win, and it would be the one that gets deposited over here. And that is why scientists don't mind the fact that this battery is going to oxidize zinc, because they know that when they get to this side, the copper 2 plus will win. And that's it.